Okay, Mike, so what we got here? We've got time domain on the top.
So we're showing the time domain on the top and a fast Fourier transform with the time domain giving us the frequency domain on the bottom. The top is showing a 5 megahertz sine wave with a peak to peak of 250 millivolts roughly, with some loss in the cables. And hit the fast Fourier transform is showing this peak here, which I put the cursor on. And as you can see, the cursor is at 5 megahertz.
Yeah, it's exactly 5 megahertz.
So our highest powered signal at this point is the 5 megahertz one, and these other signals that you'll see are the reflections of that signal, which will all be 5 megahertz apart, each slightly lower amplitude or slightly different amplitude.
So they're the harmonics, yeah?
They're the harmonics.
And they just go on forever in principle,
They go on forever,
don't they?
but the highest powered one is the fundamental one. That's the one we found at 5 megahertz.
Yep.
And so it's a good demonstration, time domain, frequency domain of the same signal.
It's a lovely demo, isn't it? Just indulge me and turn that into a square wave.
That will be an indulgence.
That will be an indulgence.
I don't know if this can do a 5 megahertz square wave. You can try.
Well, just another waveform then. So, as you can see, the harmonics have changed. Well, we've also got a widening there, haven't we?
Much widening, because obviously a square wave is a collection of many sine waves, and so therefore our bandwidth has increased, and the purity of the sine wave has decreased because of that, because of the additions of the square wave at that point. So we're going to try a triangular wave as well. See if we can do that. There we go, that's a good example.
Yeah, that's a good visualisation, that one, isn't it?
Lots and lots of harmonics, and our biggest one here is now at
Well, they're the constituent components, aren't they? So
we set it at 5. So 1 megahertz. Now, so this scope can only produce a maximum of 1 megahertz on the triangle wave. So our fundamental is now down there at 1 megahertz, which we should be able to see down here. And these are the components that make up that triangle wave, and the harmonics as such.
remarkable.
So if we had a spectrum analyzer, we could zoom in on that fundamental and actually start seeing the individual sine waves that are added together to make that triangle wave. But the resolution of this FFT wouldn't be able to get us quite there.
So Joseph Fourier's right. It's all made. The whole world is just a collection of sine waves.
It's a collection of sine waves.
Excellent. And just so you can see, we're projecting that onto the screen for the students. Okay, thank you, Mike.